Hi, in this video, we'll be continuing our study of mathematical logic, and in the previous video while we talked about the syntax itself, now we want to know the semantics, and this is done by using what we know as truth assignments. So semantics is something like meaning, and meaning, if when you do elementary discrete math, when we talk about truth table first, you already know what it is. So every proposition is either true or false, and then you form the connectives, and then you have some truth table. Well, these truth tables are basically just they're basically just functions, and if your truth table is all true, then it's a tautology. Then it could be, if P is true and Q is false, then this one is, if both are true, then and it comes out false, then it could be this. And if you just read this, you just see that's basically what the truth table is saying. So having this function resulting from this inputs result in this can be translated into this language, English language. So firstly, the set of truth values is defined to be 0 or 1. So it's either 0 stands for false and 1 stands for 1, true. Or people can also use F and T. It doesn't really matter. 0 and 1 are just numbers. And then you let the set be a set of propositional symbols, and we call W a word on A if W is a mapping of A to the truth values. So the idea is that the world consists of atomic facts, and every propositional symbol P can be interpreted as an atomic fact. So it's either true or false. So we either have WP equals to 1 or WP equals to 0. And this is known as the truth assignment. So you just take a proposition and then you assign it 0 or 1. So let F be a set of formulas. So a formula, as we already stated, is just an expression that's well formed. So it's just like you got P1 or P2, then you got the brackets, and only containing the proposition symbols in the A that we generate up, that we were talking earlier, that is satisfied by a word. Then we can associate each connective with an operation on the set E to the set E. So for negation is this, and if you're a binary operation, you're this. So the set of formulas can be just generated from the propositional symbols using these 5 operations. And although our word only must start from an atomic fact, so only propositional symbols, we can actually extend it to this set of formulas and assign the truth values according to by obeying the logical rules. And this truth value function will be unique. So the word of negating A alpha will equals to minus W of alpha. So by balloon algebra, this being 1 minus 1 is resulting in 0. And then N you can put as a product, or you can put as a addition. Implication implication alpha implies beta. Remember, we can rewrite this as not alpha or beta. Then you can, this part will just correspond to this, and this will correspond to this, and then you add them up because it's an OR. And this theorem states that for any set of proposition symbols, there can only be one extension function. So like I said, this truth value function will be unique to the set of well-formed formulas that satisfy these conditions. And these formulas can now be then summarized into the truth tables that we always known. So if this is 1, 1, then this is 0, 1, 1, 1, 1. Then so on. Let's take another example. So we have the following alpha as the well-formed formula. And we know that the world of, in this case, A will equals to 1. So this is a true proposition, false proposition. Then we let the value of, what is the value of this formula? So this formula, you just, by the definition of the extended function, because we know that there will be only one formula, so you just can work out inside first to simplify it, and it will always remain the same. So the A to C will be a false, and the B and A will be a 1. So then this will be a 0, this is a 1. Then you can check the truth table again. So B is 1 to 0, so this is 0. And then 1 is to 0 is also a 0. So 0 implies 0 is a true fact. So we can conclude that this formula is true. So the W alpha equals to 1. And if you know that W alpha equals to 1, then we say that the world satisfy alpha. So we call a set of formulas tautologically implying a formula alpha, meaning this implies alpha, tautologically implies alpha, if any world that satisfy the formulas, all the formulas in the sigma also satisfy alpha. So if we expand the definition, what you find is that if you get any world, you just take any world. So a world is just a way to assign the truth values. If for all formulas inside this set of formulas, sigma, is satisfied by the world, then it also satisfies, the world will also satisfy alpha. So we take an example over here where your set of formulas is only one, which is alpha and beta. So what does this say? So you have a formula that satisfies it. So it's W alpha and beta is equals to 1. Okay. Then is it going to be that W alpha equals to 1? Well, that's true, because W alpha and beta equals to W alpha times W beta. And this equals to 1, which only can occur if both W alpha and W beta is 1. So in that case, this is satisfied. So this is true. And we call alpha a tautology if and only if the empty set is a tautologically clear implication, tautologically implying alpha. Sorry for my English. This is in agreement with the usual statement that tautology is true for every possible world, or is satisfied by all truth assignments. Because you want W alpha to always equals 1, then the only way is that is this part inside the implication part is false. So for this to be false, The only way is for all formulas. So this one must be an empty set. Then this whole thing will be false. Then this implication is true. Then this whole thing will always be true. That's why it's a empty set. So if sigma is just one formula, you can simplify it to write without the brackets. And if both beta is tautologically implying alpha and alpha is tautologically implies beta, then we say alpha and beta are tautologically equivalent. Talking more about tautologies, we shall show a list of examples that are true. So by definition, alpha implies if and only if beta is a tautology, means this is only true if the world of alpha implies beta equals 1 for any world, then because this is just this formula, we can actually show that alpha W alpha must equal to W beta. And by definition, if you have a series of disjunctions, then you can actually add them up normally. So associative laws apply and distributive laws apply, commutative as well. Therefore, a formula of the form alpha or beta or gamma, if and only if alpha or beta or gamma is a tautology. So it basically means your associative laws of or and conjunction and disjunction is a tautology, and your commutative laws also hold, your distributive laws hold as well. So these are all tautologies, and one way to determine whether a formula is a tautology is to just compute the truth table and actually show that they are always 1. So in that case, we can actually see that double negation alpha actually is the same as alpha. So that's the law of double negation. And we can actually show a formula is a tautology by proving through contradiction. So we assume that there exists a world that satisfies the formula and actually show that that cannot be true. So it means that the set of formulas is empty. Usually, we use this technique to show an implication is a tautology, since the only case when alpha implies beta is false is when alpha being true and beta being false. So you can use this method to actually show that 6, 7, 8 are all tautologies as well. So now you know certain tautologies over here and over here. I hope you understand more about how truth assignment works. It's basically a function. So you just take your proposition symbols and you assign them your truth values. And then in that world, you just check whether the formulas are logical consequences of what you have defined. So you just extend them. And then that's how you get your truth values for all your other formulas. And the tautology is just basically something that is always true. That's all for this video. I hope you have enjoyed it. Please like, share and subscribe, and I'll catch you in the next one. Bye.